Hey guys, it's Miss Miklos, and today we are starting our final chapter of the year. And in chapter 11, we're really going to explore a bunch of calculus-based topics. So we're not going to go super in-depth in each particular topic, but it's just going to be a good foundational study for some things that you guys will see when you take calculus next year. So today we are specifically talking about a limit. So we're going to start with defining a limit. The definition of a limit is if f of x becomes arbitrarily close to a unique number L as x approaches c from either side, then the limit of f of x as x approaches c is L. And this is the notation we use to write this. And I know this sounds kind of confusing, so I just want to break it down in a few different ways. Okay, first of all, I want to talk about how do we actually read this line right here. So we read that as the limit of f of x as x approaches c, so this arrow means approaching c, is L. And I think what we can find about limits is finding a limit is a higher order thinking skill. Our actual math itself, though, is not going to be that difficult. Okay, so I think the trick is not making this more difficult than it needs to be. Another way to think of a limit is we're trying to figure out what is the height as we approach a specific x value. Okay, so we're really looking for what is the height of the function, not at that specific value, but as we approach that value, and that's kind of the weird thing. So we're going to start here with limits that exist. Okay, and there are some different ways that we can find a limit. We're going to see that we can use a table, we can use a graph, and we can also use algebra. And we're going to start by introducing using a table. And our graphing calculator itself is going to become super important, so please go ahead and get that out. And I'm actually going to spend a little bit of time in discussing how we use our calculator. So number one is asking us to use this table to estimate the limit. And it's asking us to find the limit of 3x minus 2 as x approaches 2. And the first thing that I want to just point out to all of us is that we do not care what the actual value is at 2. And that's what can seem kind of strange. We want to see what is the height, okay, which is really like the y value, as we approach 2 from the left and as we approach 2 from the right. Okay, this is from the left because these are numbers that are smaller than 2. This is from the right because those are values that are bigger than 2. So what we're going to do, we're going to substitute in these values into this expression and determine, does it appear that we are approaching a number from both sides? So I'm going to go ahead and transition now into my graphing calculator. And I'm going to show you guys two different ways we can use our graphing calculator. So I want to show us two different ways that we could do this in our calculator. I think the way that most of you guys are more familiar with would be by actually going, okay, 3 times 1.9 minus 2. And we would get an answer of 3.7, so we would write that in. Then we would repeat the process, 3 times 1.99 minus 2. And we would get 3.97. And while this is not a difficult way to do this, it can sometimes be a little time consuming. Okay, so what I want to show us instead is a way that we can use the table on our calculator. So I'm going to start by pressing y equals, and I'm going to go ahead and type in 3x minus 2. And now I'm going to press second window, and that gives us the table setup. And my guess is that yours is on auto, And that's normally what we want to be on, because what that's going to do is automatically give us x values based on the way we set up our table. Instead, I want you guys to move your arrows down and choose ask and press enter on that. Okay, what this is going to allow us to do is to ask any x value, and it's going to give us the y value or the height. So I'm going to press second table now, and I'm going to go ahead and type in the ones we want to find. So 1.9, 1.99, 1.999. So to me, I think this is actually a quicker way of finding these values because it enables us to only type in the expression once. And what I notice here, if we look at these y values, it appears that the closer we get to 2, so as we're approaching 2, it appears that the height is approaching 4. Okay, so let's see if that's true coming from the right side as well. So I'm going to type in 2.1, 2.01, and then 2.001. And we notice, okay, further away from 2, we're at 4.3, and then we get to 4.03, and then 4.003. So it does appear that from both sides we are approaching a height of 4. Okay, notice I don't care what the actual height is at 2, okay, because that's the x value we're approaching. I care what does it appear that the height's going to be as we approach 2. So that is how we can kind of manipulate a table like this when they give us specific values. Okay, so I didn't actually fill in the table for number 1 here because I was busy on my calculator, but you guys should have filled in these values as we went. And the way that we are going to go ahead and write our answer, and notation I want to stress is super important here. We're going to say the limit as x approaches 2 of 3x minus 2 is equal to 4. Okay, second example here. This time they're telling us to use our graphing calculator's table feature. So instead of giving us a very specific set of data to substitute in, we need to go ahead and use our own information and try and determine what is the limit of this function as x approaches 1. Okay, and some things that I just quickly want to point out. If we look back at problem number 1, some of you guys might be thinking, okay, what we're doing is really dumb because if I just substitute 2 in here, I would get 4. And you're correct. That is something that we call direct substitution, and we'll talk about that later on. However, if we look at one like number 2, we notice that is not the case. We are trying to find the limit as x approaches 1. If we substitute 1 in here, we get 0 in the denominator, which is not okay. So what that actually tells us is that the function does not exist at 1. However, we can still find a limit, which is what we're going to do here with our calculator. So let's go ahead and get our calculators out again. In order to go ahead and use our table, I'm going to press y equals and clear out our previous problem. And I'm going to go ahead and type in parentheses, okay, x cubed minus x squared plus x minus 1 divided by, then in parentheses, x minus 1. Okay, so looking at this, I just want to stress to us that we need to use parentheses around the numerator and around the denominator. So now I'm going to go ahead and go into the table setup. This time I want to be in auto. Our table start, and please write this down, our table start I always put as the x value we are approaching. So in this case, I care about what are the x values around 1. And delta table, we know delta means change. It doesn't need to be a specific value here, but the whole point is we want it to be something that is a small number. Okay, and the reason being, we want to see that it's getting close to a y value, so that if we're comparing x values that are close to each other, those y values are getting really close. So let me just show you. For example, your delta table might say 1 to start with. So if I went ahead and looked at my table here, looking from both sides, it does not appear to be approaching anything. Okay, it looks like 10, 5, 2, 1, error, 5, 10, 17. That tells me nothing. So if you guys ever get something like that, I would go back to the table setup and make it something a little bit smaller. So you might try like 0.01. Okay, and if I look at our table here, and let me actually go back to our table start. I want this to be at 1, so I'm going to clear this out and put in 1 again. And now all of a sudden, looking at values that are closer together, these numbers look a little more realistic. Okay, to me, these numbers appear as if they're approaching 2 from both the left and from the right. To make even more certain, though, I'm going to make this even closer. So I'm going to put in 0.001. Okay, I just wanted to demonstrate why those values are important. Okay, notice once again I forgot to change my starting value, so it's giving me these x values. So I'm going to go back to my table setup again and put in 1. Okay, so when I look at that table, when I move up, I think this is close enough for us to see that it appears that the limit of x cubed minus x squared plus x minus 1 over x minus 1 as x approaches 1 is going to be 2. And the reason why I'm saying that is because it appears that from the left side and the right side it is approaching a height of 2. So for number 2, after we put all that in our graphing calculator, I would probably go ahead and write some information here. I might make just like an XY chart for us and type in some of the info we saw. So we saw like, okay, 0.998 gave us 1.996, 0.999 gave us 1.998, 1.001 gave us 2.002, 1.002 gave us 2.004. So that's showing me that you understand that the limit as x approaches 1 of x cubed minus x squared plus x minus 1 over x minus 1 equals 2. And I did not mean to draw a line there. Okay. So number 3, this time we have a piecewise function. Okay, so I'm actually going to go ahead and sketch a graph of this, and we're going to sketch this by hand. Okay, so with a piecewise function, first of all, I'm just going to write what it's telling me to find. It's telling me to find the limit as x approaches 3 of this function, and I'm just going to write f of x there. Okay, but before we find the limit, let's sketch a little graph. So we know a piecewise function is just two different graphs that are on this same, coordinate plane that have different domains. So this first portion, okay, f of x equals 2 when x is not equal to 3, we know that f of x just means y. So if I have a graph of y equals 2 except when x equals 3, that means that there's like a little hole there at 3, and otherwise I just have this nice horizontal line. My second portion says f of x equals 0 when x equals 3, so that actually gives us an ordered pair of 3, 0. So I'm going to go ahead and plot that point. So if we look at this, it appears that the limit as we approach from the left is going to be 2. The limit as we approach from the right is going to be 2 because that is what the height is where we are approaching. So our answer here is the limit of f of x as x approaches 3 is 2. Now I just want to remind us, it does not matter that the actual height at 3 is 0. We don't care about that. We care about what does it appear that it's going to be. So now let's look at some limits that fail to exist. Okay, and before we go through specific examples, I want to show us some important reasons why limits do not exist. So it says the limit of f of x as x approaches c does not exist under the following conditions. And by the way, we abbreviate does not exist with D and E. So the first one is f of x approaches a different number from the right side of c than it approaches from the left side of c. And I want you guys to know that this information is not something that you need to memorize word for word, but you do need to know the general understanding of what it's saying. Okay, often when we talk about this, we will refer to what we call one-sided limits, and that means that the limit from the left side is different from the limit from the right side. They do not approach the same number. The second reason is f of x increases or decreases without bound. That means that it is not approaching a unique real number. It is increasing indefinitely. We can also say that it is not approaching a unique real number. Okay, that would be an adequate answer. And then the other one is that f of x oscillates between two fixed values. So we will see that it's not actually approaching one number because it's alternating back and forth between two numbers. So we're going to go through some examples here. So number 4, it says show that the limit does not exist. Okay, the limit as x approaches 0 of the absolute value of x divided by x. And I'm telling you guys, let's think about the graph. Okay, often since this is not it's not a polynomial. Normally when we have polynomials, we'll go ahead and substitute values in and use algebra. But we're going to go ahead and graph this. So go ahead and get your graphing calculator back out. I'm going to press y equals and clear out my old graph. And we need to graph the absolute value of x divided by x. And most of you guys have probably never graphed absolute value before. So where we find that, if you press math and then move up over to the number menu, that very first option, ABS, means absolute value. So I'm going to do the absolute value of x divided by x. So I'm going to press zoom 6, and that's just going to go ahead and sketch a graph for me. And some things I notice here as we are approaching from the left side, it appears that we are approaching a height of -1. As we approach from the right side, it appears we are approaching a height of +1. So this is a case where my one-sided limits do not match. If I wanted to look at a table of this, okay, I'm going to go table setup, and I'm going to make my table start 0 because that's the x value we're approaching. And then if I look at my table here, it makes it really evident, okay, everything to the left is at -1, everything to the right is at +1. So that means that the limit here does not exist. So as we saw from our calculator, with this particular graph, we were approaching different numbers from both sides. So we're going to go ahead and say the limit as x approaches 0 of the absolute value of x over x equals D and E because, and I want to stress, we never just say D and E on our own. We need to supply a reason. And I'm just going to write it because the one-sided limits do not match. Okay, that would be an adequate reason for you guys to go ahead and give. So number 5, once again, we have this value, determine whether or not the limit exists. If we went ahead and plugged 0 in this case, I would get 1 over 0, which gives us a problem. So this is another one I'm going to rely on my graphing calculator for. I'm going to go ahead and graph this. So I'm going to press y equals 1 divided by x squared. And then I'm going to press zoom 6 to give us a sketch of that graph. And I noticed some weird things here. Okay, as we get close to an x value of 0, I can't really tell what the height is. So some things that we might do, I can press window and I can change the window. So, you know, maybe it's reaching a height that I just can't see. So what if we made like the y max 30 and I graphed that? Okay, what I'm seeing is that it still looks like it's increasing indefinitely. I could change my window to something else, like, I don't know, we could do it anything. Let's do like 300. Okay, and when I sketch this graph, okay, I can't really tell what's going on here. So I might go to my table setup. We're seeing as it approaches 0, so I'm going to type in 0. And then I'm going to do second table, and I definitely noticed some things here. Okay, on the ones where we found a limit, these y values were all really close to each other, but here we can see that there is a huge gap. Okay, we know 1e to the 6th is scientific notation for 1 times 10 to the 6th power. So what this is telling us is that the limit does not exist because the function is increasing without bound. The reason why it's increasing is because these numbers are getting bigger as they approach 0. So for number 5, I'm going to go ahead and say the limit does not exist. And I would accept 2 different answers. You could say because the function increases without bound. Or the other one that I would accept was does not exist because it does not approach a unique real number. So moving on here to number 6, it says determine whether or not the limit exists. So here I have a trig function, and so I'm just going to make a quick note that whenever we see something that is trig, our mode, if I can spell mode there, M-O-D-E, should be in radians. So we're going to transition back to our calculator. So as I said, we need to go into our mode and make sure we're in radian. Remember, if you're not, you would just use your arrows and then press enter and it would be highlighted. So I'm going to press y equals and go ahead and graph our particular function here, which is sine of 1 over x. So when I press zoom 6, this is what our graph looks like. And quite honestly, it's kind of tough for me to see what's happening as we approach 0. So some things that we can do, and this is just a good review, we can zoom in. So I press zoom in. The cursor here is telling me that that would be our new middle. So I'm going to press enter. And it's zooming in our graph. So it's like this picture, now we're just looking at it at a different angle. That still doesn't show me much. So I'm going to zoom in again. And this time, we're going to see something kind of crazy happen. Okay, see how it's just going up and down so quickly? Okay, that to me shows that something weird is happening. In fact, if we go ahead and look at our table, notice that our y values are alternating between positive numbers and negative numbers. Okay, that is showing me that this is actually oscillating between two different y values, which means that the limit does not exist. So based on what we saw in our graph, we would say the limit does not exist because the y value oscillates. Or we could say, once again, that the limit does not exist because it does not approach a unique real number. So I just want to stress to you guys that this terminology, I'm not going to be like, you didn't put in one of the words or anything like that. It's really the general idea for it. So we kind of saw 3 different examples here, and I just think it's helpful for you guys to know that this was like number 4, number 5, and number 6. So in case you guys ever have a question as to what those look like, you can refer back to your notes and actually see that in action. So the final thing that we're going to do today is talk about direct substitution. Now, unfortunately, this does not always work, but today it's going to work, which is great. And the explanation for direct substitution, we've seen that sometimes the limit of f of x as x approaches c is simply f of c. We saw that in our very first example. When I substituted directly into the equation, we got the height, which was the actual limit of that function. So some basic limits. Okay, once again, these are things we don't need to know the names of. We just need to know how to use them. Okay, our first one, it says the limit as x approaches c of b is equal to b. This makes sense. Okay, what it's saying to us is that this is a horizontal line. So as x approaches any value on that horizontal line, that y value is our answer. It's the height. Okay, the second one, okay, x just represents a linear equation. The limit as x approaches c, we can just substitute c in for x, and that is our answer. For number 3, it says the limit as x approaches c of x to the n power, we can substitute c in and get c to the n power. Our final one, if I have a radical, once again, I can just substitute c in for x, and that would be our limit. Okay, some properties that I just want to point out here, and these are terms you don't need to memorize, but I'm going to point them out today. I just want to stress we're doing very, very simple limits today. When limits get more complicated, these become very, very important. So it might seem kind of dumb that I'm talking about them on something simple today, but hopefully it's just showing us that when we get to some more complicated examples, we can break it down and make it simple. So our first one is scalar multiple. We know a scalar is just multiplying by a constant value. So what that means, the limit as x approaches c of a constant value times a function is just that constant value times the limit of that function. So we can basically factor that constant out, find the limit, and then multiply those numbers together. These next 3 are all kind of the same in the sense that if I am adding, subtracting, multiplying, or dividing limits of functions, instead of having to try and add them together first, we can split them up and find these 2 limits separately and then add the limits together. Or instead of multiplying, we can find those limits separately and then multiply the limits together. Same with dividing. Okay, we can find them separately and then divide them. Lastly, our power property, I can find a limit and then take it to the power rather than trying to expand this particular function. Okay, so these problems say find the following limits using direct substitution. What properties are being used? So for A, it says the limit of x squared as x approaches 4. It appears that we are using direct substitution here, And it looks like I'm going to use that power property because I see that exponent. So all we're going to do here is do 4 squared, which is 16, and that is our answer. For B, this would be a scalar multiple. Okay, and what that means is I'm going to do 5 times whatever the limit of x is as x approaches 4. We know that that is just 4. 5 times 4 is 20. For C, this is our quotient property. And I'm just going to write quotient. So we're going to find these two limits separately and then determine what they are. I know I have tan of pi divided by pi. Tan of pi is one of our quadrantal values. I know that it's 0. If you put that in your calculator with radians, it would give you 0. So our answer there is 0. Letter D. Okay, here I have a square root. Technically, a square root is a power because we know it's like a 1/2 power. So I'm going to go ahead and just use direct substitution with my x and then take the square root of that, which would be 3. For E, this is our product property because I'm multiplying two limits together. So I need to split it up. And I'm going to do the limit as x approaches pi of x times the limit as x approaches pi of cosine x. So that first limit is x. I'm sorry, not x. It's pi times the cosine of pi. Okay, we know the cosine of pi is -1. So our answer here is -pi. Okay, and lastly, just to show direct substitution once again, I am substituting this in. This is a power property because it's saying I can find this limit and then square it. Okay, so I have 3 plus 4 squared, 7 squared, which is 49. Now, this was probably, for you guys, the easiest part of the day. Now, when it becomes tough is going to be next time when I use direct substitution and I get something like 0 over 0. We call this indeterminate form. And that's going to mean that we are going to have to use a different method to solve it algebraically. And we will hit on that next time. But for now, hopefully this just gives us a good idea about what a limit is and showed us a number of ways using tables, graphs, and algebra that we can determine the limit of a function as we approach a specific x value.